So hi, this video we're gonna looking at pressure changes with the depth. So come up with a very important equation, basically P equal to rho GH. Okay, let's take a look. Imagine if you went to scuba diving and the deeper you go, we feel more pressure, right? You know, the pressure increases. So anything you go deeper, in that situation, the pressure increases. For example, here that shows this linear increase with the height. And for example, here at point 1, which is interface between air and this liquid. So in that situation, the pressure right here at point 1, that's taking out as atmospheric pressure. And then when you go down to inside of this liquid, when you go deeper, the pressure increases in this linear pattern. So this pressure is going to be the atmosphere pressure already, then plus this rho GH. So what's rho? Rho is going to be the density of this liquid. G is our gravitational coefficient, 9.81 meter per second square, or 32.2 feet per second square, right? H is going to be the depth. So pressure in a liquid increase linearly with the distance h here from the free surface. So that's a very important equation here. P here is equal to atmospheric pressure plus rho GH. All right. Now let's look at something like this. So we discussed the pressure in a liquid increases with distance. However, if it's not a liquid, if it's gas, if it's a room filled with gas, however, this variation of pressure with height is going to be negligible. Unless you are talking about like a hot air balloon going like thousands of feet high, then yes, that's going to be different, a pressure difference. But however, just for example, in a room, regardless it's on the top or bottom, the pressure left and right, they're all going to be similar. The pressure will be similar. Now let's look at this slide. This is a very odd geometry, but you notice A, B, C, D, E, F, G, those few points here, regardless where, what shape they are at, they all share the same distance from the free surface there. They have the same height, same h. So using that formula, P atmosphere pressure plus rho GH, they are going to have shared the same pressure. So the pressure is the same at all those points if they are on the same horizontal plane, regardless, the geometry, right? As long as they are connected by the same fluid, because rho is the density of the fluid, okay? So that's going to be this video is going to be pressure. It changes when H goes higher. P equal to rho GH. All right, now we're gonna looking at something more about this P equal to rho GH, and we're gonna look at its own unit. So pressure rho GH here. So we talk about rho is the density. What's the density unit if it's in a SI system? In a SI system, density is mass over volume. So in that situation, mass is in kilogram and volume is in meter cube. So kilogram per meter cube, that's going to be your density, right? Then G, we're talking about G is gravitational coefficient. So G is going to be 9.81 meter per second square. And H is going to be the distance, so that's going to be taken unit of meter. Now, what we're going to do is trying to find out if this equation satisfies the dimension homogeneity. So we know the left-hand equation, pressure in SI system is Newton per meter square, or Pascal in short. Then the right-hand equation, density, is mass kilogram per meter cube. G is meter per second square. And H is, oh, I think I made a mistake on H here. I wrote it meter cube. That's not right. So H is going to be just meter. So times meter. Now let's take a look. We're going to manipulate this equation a little bit. So kilogram meter per second square. So basically it's mass times acceleration. MA, force equal to mass times acceleration. So that's going to give us a unit of Newton because it's force, right? Then when we cancel out 1 meter, so it's going to be Newton meter square. So the left and the right hand side does satisfy in terms of dimension. You can do the same check using the US system as well, and the answer would be yes, it's dimension homogeneity. So that's P equal to rho GH. So in the next video, we're going to discover some concepts on manometer and using this basic concept. All right, I'll see you in the next one. Bye.